certain memory address through to analyze and bin the different types of faults and failures we're seeing, that script ran 8 to 9 hours. And after those 8 to 9 hours, we figured, oh, there was an error in the script. Okay, let's run it again. Right? So this is not a very good idea to do research. Right? So we started before that already developing different types of analysis software, and I'm going through a little bit of these. So this is Raven. This is actually our oldest tool that existed already something like almost 10 years ago, which was actually originally developed for Jaguar, I think, for the last Jaguar system, and then adapted to the Titan system. It basically has sort of a front end where you can click and select nodes, you can select time intervals, and then you can select event types, and you can visually inspect. Basically, you can figure out are there any sort of correlations, right? So here you can see a little bit, just tracking my time here, how this works. So you basically have sort of here, you see the event occurrences, here you see how applications are basically allocated, and then you can do some analysis, some histograms and things like that. All nice and interesting to do. The problem is this doesn't scale, right? So realize we may operate here on several terabytes of data, right? So, and this doesn't work. And so we started within this project developing different tools and things like that. So this was Loggator, developed at Argonne National Lab, which basically looked at the logs and started doing statistical analysis over the logs a little bit more in a more efficient way, doing spatial correlation, for instance, but also temporal correlation. The next one, also from Argonne National Lab, was also a visual tool. It was sort of a next generation visual tool where, again, we had sort of an interface where we could select nodes, events, also applications, and then looked at what's going on in the system, and those arches here are actually autocorrelated events, where basically the system in the background is actually correlating already events and showing them. This is already sort of a first attempt in trying to basically automatically do something in the background. And then, so there's a little bit of a blow up of this picture. And then we started looking at, as I said, we did analysis of applications, how they behave. And at Lawrence Livermore National Lab, we basically developed this Refine tool, which is a fault injection tool, which allows us to inject faults into applications, but into the backend code. Most fault injection tools either inject them right here in the intermediate representation or in the machine code. And the machine code is typically at the runtime using PIN. And the problem here is that we saw when we injected failures into the intermediate representation, it was the compiler actually optimized those faults away. So we actually didn't inject failures, they were optimized away. So this is actually the most accurate and the fastest way to actually inject failures into an application. And Lawrence Livermore National Lab, they're actually currently working on identifying different computational patterns within applications and then associating reliability characteristics to these application patterns, basically. And that's actually quite substantial work what they're doing over there. And now at Oak Ridge, we have a little more time to talk about that. What we're doing is looking at the online analysis, and when we started looking at that, we realized that we did the offline analysis already in a way that doesn't facilitate the online analysis. So we had to start almost from scratch again. And we started looking at big data, right? Big data analytics, because at the end, we're basically created our own analytics problem here. And we basically set up a system at Oak Ridge where we used an internal cloud infrastructure at Oak Ridge to deploy Apache Cassandra, Apache Spark, and basically ingest the system logs into the Cassandra database, already pre-processed, the events into a database, into database tables. The tables are organized sometimes by location, sometimes by event. There's always time series. And then we basically use Spark to do analytics over this database, basically. And using then, for instance, the Jupyter Notebook as sort of some type of front end, we can actually do very good analytics using this type of framework. And this surprised us a little bit that this works so well. We started doing machine learning over the failure data. We are starting doing pretty advanced statistics. We started doing principal component analysis, looking at information entropy. So trying to, for instance, figure out, okay, what information is in this system log? How does this information change over time? What information is actually essential here? And what information provides us indicators for the health of the system? So we just finished up a paper and submitted it on Sunday, where we basically came up with sort of a new way to analyze system health by just finding a simple indicator, a statistical indicator, that basically tells us something is wrong with the system. Now, what is wrong with the system then is still up to a separate analysis. But having already an indicator that tells us something is wrong on the system, and you add a live indicator, it's actually very interesting. So this is actually how we do this offline. Now, how do we do this online? Online, we basically ingest the data directly via Kafka and Spark Streaming into the database, and Spark Streaming already does some analysis, and then publishes the event again, triggers other analysis, maybe it triggers users, maybe it triggers system operators to basically then do more analytics over the data that's coming in, right? And that's what we're currently working on. It's actually a relatively large team that's currently working on this, looking at all kinds of interesting aspects to it. What I want out of this is, for instance, a notification about ongoing system health crisis. We are already there with that, with the paper we just submitted. And the more difficult one is a notification about root causes of application aborts. So that we basically have then an online system where the application programmer who just ran a job and the job failed, he can go to that system and just give, that job ID, and gets a return back that basically says your job failed because of this. This would be a great system, but we're still quite far away from that, right? Another interesting aspect would be just give the job ID and the system tells you back nothing was wrong with your job run or your application is at fault, right? So that's something interesting as well. So with that, I'm just summarizing a little bit what we have done so far. We have identified, categorized, and modeled the fault, error, and failure properties of Department of Energy supercomputers. We have created a fault taxonomy, a catalog, and models of the conditions in current systems. We have developed a number of tools and frameworks for this. There are tons of publications out of here. We have 2 DSN publications just last week, 2 SC17 publications, a Mascots, a DSN 17 paper, CC Grid 17 paper, and a few workshop papers, and then also an IPDPS paper in 2016. We're still in the process of actually publishing way more results. Unfortunately, some of our supercomputing papers got rejected. And as I said, ongoing work focuses on the error propagation studies with applications, doing the patterns basically, the online analysis framework at models, and then the refinement of instrumentation points, which is also important. But at the end, this class mostly contains mostly debugging. It's what is interesting and necessary and what is not. What else do we need to add to that? So with that, I'm closing up, and if you have any questions. See you yeah. There was a question up there.
Yeah. Thank you for this wonderful talk. This is actually an impressive amount of work. Maybe we can have some questions. I think you can press the mic button.
You start off by saying you showed a chart of mean time between failure, and it showed, I think, systems getting more reliable over time. Anyway, I'm curious if you have any anecdotal information from your user communities on these big machines as to soft failures. So the ones that are insidious and supposedly going to happen more frequently on the new platforms, and I'm curious if you see any trend on the newer platforms with soft failures.
Yeah, so to correct you, so you mean soft errors, right? So, and you mean data corruption more precisely, yes. So yes, we have seen that. In fact, at Oak Ridge we had what was the system called? GEA, yeah, GEA system, which was actually doing climate and weather modeling. And during the last year of operation of that system, we ran some codes, and they were showing very odd data. And we realized after running some of the codes that there were some gaps in the system, and it took us, I think, several months to figure out that the processor was aging, and the guard bands inside the processor were just getting old, and we got bit flips within the logic of the processor. So that's, for instance, one something that we did see at Oak Ridge directly.
Thank you. I have maybe just a small comment, because so you said the error were coming from the processor, not from the memory.
Yeah.
The memory was protected by ECC.
Yeah.
I imagine. Okay.
Yeah.
I think you can press the mic button.
So I have two questions. I'll repeat James's question, which is the MTBF charts you showed seem to show that the MTBF increased with time, which means the systems were getting more reliable, but you seem to imply that they were getting less reliable with time.
So there are a number of different jumps, right? And jumps are always bad, because we base our checkpoint intervals on the initial mean time between failures. So when you see the system getting more reliable, you're actually checkpointing for nothing. You're basically checkpointing way too frequent. That was one problem. And another problem was that sometimes we just saw drastic returns from basically it's jumping back to a lower mean time between failure, right? So that basically is something that we also didn't expect, right? So we saw both, basically systems becoming more reliable and systems becoming less reliable, right? And I'm mostly focused on becoming less reliable, because that's more of a concern than the more reliable. More reliable just means we are wasting more time on checkpointing. Less reliable means we're actually losing work.
So as a follow-up question, at the very start you seem to imply that there was a phase where people were really worried about resilience, that the sky was going to fall, to paraphrase what you said. But you didn't think that that's necessarily the case, that the systems could be optimized to be more reliable. But at the same time, your studies show that we are far from understanding how systems face failure. So where is the gap there? Because if we don't even understand the resilience or reliability of systems, how can we be confident that they will be reliable?
Yeah, it's a very good question. So we understand some of it. And it's an ongoing struggle, not only of understanding, but also of a discussion with vendors, because we have also differences in opinion. So vendors will always tell us their system is reliable. And then we run them for 2 or 3 years and it's not. And then we look what is actually failing, and it's typically something that the vendor didn't expect. Right? So at one of the Jaguar systems we had, the Cray Jaguar systems, we had the problem that voltage regulators were blowing out. The voltage regulators were 5 times redundant. All 5 basically on a computer blew out one after another. The vendor never expected that. It's a $2 equipment that the voltage regulator, right? So basically a $10 failure basically resulted in a compute node outage. And in that particular network, a compute node outage meant that the router that's attached to the compute node was also going down. And since the vendor never expected that, the routing capability was static, which basically meant we had to reboot the entire system after a compute node failure just to reset the routes, to reroute around that single node that failed. So this shows how we over time learn what's going on these systems and then feed that back to the vendor. And the next generation, we never had that problem again because the vendor thought about it. Sorry?
That once the systems change in the next generation, a new set of problems arise.
Yeah.
So it's a constant